This is now we have got the another topic, that is Lagrange multiplier method, and how it is represented. Lambda. By lambda we represent our Lagrange multiplier. Okay, and this is its symbol. Okay, and here also we have a x random variable that is has the limit from x1 to xn, and we have f of x. We call this thing as f of x, as you know that f of x is a function. F is a function of x, and L of j, this is the we have this is Lagrange function, and it has the limit from j has the limit from 1 to p. Okay, this is the Lagrange function of x, and equals to 0, and where j is the function. J has the limit from 1 to p. Okay, and we have to find this function in the form of this x and random variable x and lambda. Lambda is Lagrange multiplier. We have to find this joint probability of L of x and lambda. So what would be the formula to find this joint probability of L of x and lambda? So we have f of x, this f of x which has x from x1 to xn, and we have in n plus the other thing, the lambda thing, Lagrange multiplier. So how it can be represented? It would be from j going from 1 to p, lambda j, L j of x. So what is j? J was here Lagrange function. It is j, and it has a limit from 1, j going from 1 to p. It has a limit of 1 to p, and Lagrange of j, L j of x, like the function of x here, Lagrange function of x here, and Lagrange multiplier here. So this is the way to write it, and let's see how we're going to find the Lagrange multiplier, how we are going to apply this Lagrange multiplier, and how we find the Lagrange multiplier and the f minimum and r1 r2 reliabilities, and f minimum of the of our RBDs, or the RBDs can be in the form of parallel, or they can be in the form of series. So how we are going to find this? We are going to find our reliabilities. So now we have got this equation, and how we get it, I have told you that this is the Lagrange. This is the way of writing this Lagrange multiplier. This is the joint probability of this. Okay, now what's next? Okay, now I say that we have an RBD. We have a RBD of parallel, that is R1 and R2. We have got two reliabilities in the form of parallel, R1 and R2. We have to find these reliabilities. So how we are going to find through the Lagrange multiplier? Let's see. R1 and R2. You know that we can write R1 and R2 in the form of like this: 1 minus R1, 1 minus R2. So this is this way, and when we solve these things, and we have f of x, here it is written we have f of x. And what is this f of x? F of x is the function of x, and it has the value r1 plus r2. You remember in the upper part we say that we have f of x that has the value c plus and c plus plus c1 plus c2. F of x has c1 plus c2, and we suppose that c1 is 100 r1 square and c2 is 200 r2 square. So these are the things that we are supporting. F of x is a function which has a cost of c1 and c2. So the same thing is happening here. F of x is a function that has a cost of c1 and c2, and c1 and c2 are the reliabilities, which has r1 reliability and r2 reliability. That's why we are finding this. We are finding the cost. We are finding the reliabilities of r1 and r2 on the basis of like this. So now we are supposing our r1 is 100 r1 and r2 is 200 r2. Okay, so here it is our cost of 100 and 200 r1 plus r2. So this is we can suppose it, we can write anything like or either what our cost is given to us, like we maybe have something different, we maybe have some different cost here, c1 is different, c2 is different. So we can write it like this, but the way to write f of x is in the form of c1 plus c2. So you got it how it comes here, because f of x is a function of x which has a cost of c1 and plus c2. Okay, yeah, now it's here, we have to find the reliabilities of these. So here it is the method of doing our reliability. We take it like this, in the form of when we are in the we have a RBD of parallel. What we did, 1 minus this multiplies by this and this multiplies by this r1 multiplies by 1 minus minus plus r1 r2. So and that's just solving, it's just a simple solution, simple calculations, the sign changes, 1 cancels out and this remains r1. Oh, you can write it r1 plus r2 minus r1 r2. So now we got this. Now we have L is our Lagrange. Remember, L is our Lagrange function of x. What we have this, we have r1 plus r2 minus r1 r2. Remember this, and minus 0.7. We take it this and also 0.7, because you remember we have given the constraints from 0.7. We have starting constraints of r1 and r2 from 0.7. So that's why we have right here minus 0.7. So this is the way of writing our Lagrange function of x, r1 plus r2 minus r1 r2 minus 0.7. This is basically we are doing the Lagrange multiplier method. Okay, and how we can now represent our equation in the joint probability. Remember this, we have write it here in the above. We have a joint probability of Lagrange multiplier as f of x plus, and this sum from j going from 1 to p and lambda j and lj of x. We have this sum. So how we can write it in the form of this joint probability? We have f of x. Yeah, we have find out of our f of x. What it is, we have our f of x is something, okay, yeah, f of x is something like this. It's 100 r1 plus 200 r2. This is our f of x. We have find out. It's no, we have not find out, it's given already, because we know that our f of x is the sum of cost 1 and cost 2. So it is in the way of like this. So it comes here in the place of f of x, see, plus what we have, plus we have f of x is being written, and plus we have this. So it can be written as lambda j of x. Okay, j going from 1 to p, so it can be written in the form of lambda j of x. So lambda, oh sorry, L of x, lambda L of x, because we have L now, we have L is the function of Lagrange multiplier. L is a Lagrange function, so we can write it in the form of lambda L of x. So L of x, we say that it is this, r1 plus r2 minus r1 r2 minus 0.7, it is this. And by writing the values, by keeping the values in the equation 1, we name it as equation 1. Okay, so now we keep the values over here for our joint probability, 100 r1 plus 200 r2 plus lambda L of x. And what is L of x? L of x is here in equation 1, r1 plus r2 minus r1 r2 minus 0.7. So this is our joint probability of a system which has a cost of 100 r1. First cost is 100 r1 and second cost is this 200 r2. We have a system, we have an RBD that is in parallel. Two reliabilities are present, they are in parallel, which has a cost of, we have cost 1 of this, cost 2 of this. So we can write its joint probability of Lagrange multiplier in the form of this. Now what we are going to do, let's see, we are okay, now we will multiply this lambda r1 lambda r2. Okay, and this lambda will be multiplied by this, and this lambda will be multiplied by this. We'll solve the brackets. After solving the bracket, what we got? See, this remains the same. It got solved and so on. Okay, got it? Now what's next? What we are going to do now? We are going to derivate our this joint probability. We do derivation in the function for r1, for r2, and for lambda. When we do derivation in the form of r1, when we derivate our r1, what we got here? R1 is present, so it would be 100. 1. This is the way of doing derivation. Yeah. 200, no r1 is present, so this would be 0. r1 is present, it would be 1. Derivative of something, that r1's derivative would be 1, you know that. So only lambda remains. This becomes 0, and what is here? Lambda r2, because r1 is here, so it would be 1, and it will become lambda r2. Only in derivation, you know that now, only we will take the values where our function is present, where our r1 is present. Only those values will be taken and being derivated, and the other ones which has this r2, they'll be considered, they'll be neglected and 0. Okay, so now what's next? Now what we did, 100 plus, we took this lambda out and common, and see what happens. We got the value for lambda, and lambda, you remember, is our Lagrange multiplier. So all these things we were doing for finding our Lagrange multiplier, that is lambda, and we have found a value for an equation for this our Lagrange multiplier, like this, in the form of minus 100 over 1 over r2. The same we will be doing for this r2 function. We will derivate it. This thing will become 0. This would be 200. This will become 0. Here it would be plus lambda, and here it would be r2 will be 1, so minus lambda r1. So in the same way, we have got another value for lambda, that would be 200 over 1 minus r1. So we have got two equations for lambda. The first is minus 100 over 1 minus r2 minus 200 over 1 minus r1. We have got two equations for lambda. What we are going to do? We are now going to compare these equations. When we compare these, and this is this in the form of lambda, we derivate our equation in the form of lambda. So when we derivate it, it's so easy. This would be 0, this would be 0. Here it would be r1, because lambda would be 1, lambda would be 1, so r2, lambda would be 1, so r1, r2, and lambda would be 1, so 0.7. So it becomes the same thing, r1 plus r2 minus r1 r2 minus 0.7. Now we are going to compare our lambdas, our Lagrange multipliers. When we compare them, this cancels out, this cancels out, this 1 over 1 minus r2 remains here, and 2 over 1 minus r1 remains here. Now what we are doing simple calculation, simple multiplication and multiplication and minus and subtraction and addition. So 1 minus r1 equals to 2, 1 minus r2, this comes here, and 2 goes there, it becomes minus 1 minus r1 equals to minus 2 r2, and this comes minus 1, and minus r1 here equals to minus 2 r2 remains here only. And what happens next? We got a value for r1. See, we say that we were going to find out the values for our reliabilities. So we find a value, that is r1, and its value, what we got here, is 2r2 minus 1. By doing our calculations, we found a value, an equation, you can say an equation for r1, that is 2r2 minus 1, and we name it as equation 2. Yeah, okay, we name it as equation 2. Now what we are going to do, put value of r1 in equation 1. Put value of r1. We have got this r1 value, and it say to put it in equation 1. And where is our equation 1? Let's have a look. We have, yeah, we name it this equation as 1. So now we have to put our r1 value in this equation. So r1, see, okay, we put it here, that is r1 comes here plus r2 minus, remember r1 and r2, so r1 comes here, multiplication r2, and minus 0.7 equals to 0. So we create our value of r1 in equation 1. So by doing simple calculations, this would be opened, and this comes here, and this is gonna multiply, only this is going to solve. So 2r2, and this becomes square, minus minus plus r2 minus 0.7 equals to 0. So this is the thing that we find out, and see, we can see that is there anything that is subtracting or adding. So yeah, we have 2r2 plus r2 and plus r2, so it would be added and would become 4r2, and we have minus 1 and minus 0.7, so it would be minus 1.7, and this minus 2r2 square remains as it is, equals to 0. Now we can take 2 as common, because 2 is also here, 2 is also here, so we can take it as common. When we took it as common, 2r2 remains here, minus, we don't have any 2 here, so it would be divided, minus r2 square equals to 0. So this 2 comes over here, and 2 multiplied by any number, multiply or divide by 0 multiply or divide by any number would be 0. So what remains, here is the equation that remains, and you can see that we can do this equation in the form of this. You know, we have a formula when we have ax square minus bx plus cx equals to 0. So we are getting this thing in the form of this. So now what we did, we find out our equation in the form of this. So this can be written as, we have a formula to write it as minus b plus minus under root b square minus 4ac over 2a. So by substituting our values in our formula, we have a equals to 1. See, we have a, this is a, this is b, and this is c. You know that a is 1, b is minus 2, and c is 1.7 over 2. Yeah. In the same way it is written here. So by solving this quadratic equation, you know that this is called the quadratic equation formula. Okay, we have when we have this type of equation, that is in the form of ax square minus ax square minus bx plus c equals to 0. So that is the quadratic equation, that is the quadratic equation form. And to solve that quadratic equation, we have this formula to we can solve it, the quadratic equation, with the help of this formula. So now we put these values in this formula, minus, and in the place of b we have minus 2 plus minus b square, that is minus 2 whole square minus 4ac, a is 1 and c is 1.7 over 2, bracket close, under root, and over 2a, and for 2a we have 1, so 2 into a, 2 into 1. So by you can use the calculator for this calculation, and we'll get two values for R2, that is 1.387 and 0.6127. So we have got these two values, and we will be going to take the value 0.6 because our reliability is bounded between 0 and 1. So we won't be taking this one R2 because this is greater than 1. So we will be taking 0.6127 because our reliability is bounded between 0 and 1. See, it's written here. So we will be taking R2's value like this. This one value we will be taking. Now what is the next step? So after taking, we did it till here. So after taking R2 as 0.6127, what we have to do now? Put in equation 2. So where is our equation 2? We named our which equation as 2? Let's see where it is. Okay, yeah, here it is. R1 equals to 2R2 minus 1. This is our equation 2. So we will keep the value of R2 and we'll find the value for R1. Okay, so we have done it like this. 2 R2 in the place of R2 we have 0.6127 minus 1. So by calculating we will be getting 0.2254, and we can easily find our F minimum, that is 100 R1 plus 200 R2. Remember, we have F minimum as 100, F is 100 R1 plus 200 R2. We put our, yeah, you can see that we have our f of x equals to R1 plus R2, that is 100 R1 plus 200 R2. So now for finding F minimum, we will keep values for R1 and R2. So R1 we have 0.2254 and R2 we have 0.6127. So by multiplying and adding both the terms, we will get 145.08. So this is our required F minimum.